Hi, Nick.
Hey Tim, how's it going?
Good to see you.
Yeah, great to see you. Could you try sharing your screen just to make sure that works smoothly?
Let's do it. How's that look?
Can you go full screen?
Yeah, sounds good.
Okay, great.
Seems all right.
Yeah. Are things in Princeton?
Pretty good. We just had a going away event for Spencer Hill because he's
Yeah.
switched to City College. That was fun. Got a vintage Isaac Held story,
Yeah.
which was new to me. Um, yeah, so I think it was a great send off for him. But of course, I'll selfishly miss having him in the community.
And what's your title, or how should I introduce you?
Um, my title is Science Manager. It's kind of a weird name. Yan-Ting,
Nick,
how's it going?
Hi, Tim. I'm
Nick,
reviewing.
did you see the file?
Yeah, thanks.
Okay, good.
Tim, we'll probably have you go last, and Yan-Ting, if you could go first.
You go first.
Yeah.
Okay.
And
Oh.
could you actually share your screen now just to quickly test?
Okay. Okay. I should be able to do that. Does it work?
Could you go full screen?
Okay.
Yeah, looks great. Okay, I think we're just missing Luke. Hey, Christy.
Hello.
Hi, Christy.
Hello.
Still don't see Luke.
Yeah, I would probably go ahead and send him a reminder.
Okay, we might get started. If Luke's not here soonish, then Tim, I might ask you to go second, if that's okay.
I see. He just logged in.
Okay. Luke, are you there?
Yep, I'm here.
Okay, great. So we'll have you go second, if that's okay.
Oh, sounds good. Gotcha.
Okay, so I'll get started. Welcome everyone to the 27th ECS and Cloud Feedback Virtual Symposium. Before we get started, we have kind of a big announcement. It's a kind of bittersweet session. Our founders, Andy Dessler and Christy Borchescu, are stepping down. This is really their initiative and their baby, and they started Symposium, which I think the whole community has really benefited from. And so, yeah, I guess a virtual round of applause for them, and please thank them for coming up with this and for they've been doing a lot of legwork behind the scenes to keep it going. Okay, so I'll just go over the format again for people who are new. We'll have 3 AGU style talks. So, about 12 to 15 minutes with questions after each. And if there's time at the end, we'll have a short general Q&A after the last talk. If you have questions or comments, please type them into the chat at any time. The chats get posted at the end of the symposia, and it's normally pretty active, so definitely keep an eye on it. And you can also ask questions live. Just raise your hand and we'll unmute you. Yeah, so right now the executive committee is me, Shia, Andy, Christy, and Jonah. Jonah's stuck on a delayed flight right now. Since Andy and Christy are stepping down, we'd love to have 2 new members to join the committee. So please get in touch if you're interested in helping to organize. It's not a huge time commitment, and I think it's a really great service to the community. Community contacts, past videos, mailing list sign up, and more is at our website, which I think Andy intends to keep hosting, but we need to figure that out. So with that, let's get started. Our first speaker is Yan-Ting Chen, who's a graduate student at McGill working with Yi Wang and Tim Merlis.
Okay. So I'll get started. Okay, so thanks for having me. Today I'm going to share a project about the instantaneous CO2 forcing. And I think most of people in our community knows that the CO2 usually traps the long wave emission, which means an increase of the energy budget of the Earth system. But we are going to focus on a slightly different part. We are going to see like in what kind of condition can the CO2 forcing be low or even negative. And by definition, the CO2 forcing here is simply the instantaneous forcing. So there is no any feedback or adjustment included. So this some low or even negative CO2 forcing does not necessarily translate to a surface cooling. So okay. So before I get into our result, I would like to give an overview of the instantaneous CO2 forcing. So the figure below is based on the long-term average of 19 years CO2 forcing calculation. The sign convention is downward positive. So a red means CO2 traps long-wave emission. And we see that in the Antarctic, there is a difference in the sign, which means that CO2 forcing is negative, so it enhances the local long-wave cooling. And in our previous paper, we have shown that such forcing variability for both spatially and temporally, they can be well captured by a very simple predictive model with the information of just the surface temperature Ts, the stratospheric temperature T at hectopascal, the water vapor, the column water vapor, and also the cloud radiative effect. And all the quantities in this equation are normalized by the global mean. So this is a long-term average one. We already see that in the Antarctic, the CO2 forcing can be as low as maybe like minus 0.5 parts per meter square. But this is based on a long-term average, and we know that temporally, if we focus on a shorter time scale, all the variable in this equation shows a larger deviation from the global mean. So I would like to show some snapshot in a short video about how variable the CO2 forcing is. So let me see how I can have this. Okay, so the sign convention is same as before, and we can see that even outside of Antarctic, we can also spot some region with a negative forcing in both the deep tropics and also occasionally in the polar region, like you can see in the Greenland and the Arctic. And we found that in the time slices and these regions with a negative CO2 forcing, they are either with a very warm T10, the stratospheric temperature, or a strong cloud radiative effect at the TOA. And so how frequent does this negative forcing happen? It can sometimes go below minus 1 watts per meter square, and half of time in the Antarctica, and also around 3% of time in the tropics can show a negative forcing. So how to explain this in the first place? We first look at a gray atmosphere, which is a simplified view. So if we approximate the air emission into like one effective emission layer, in the control climate, we can assume all the air emission comes from a particular layer. But with more carbon dioxide, this emission layer is always elevated to a higher part of the atmosphere. And when this is combined with a left rate, which is usually positive in the troposphere, it means there is a decrease of the emission temperature. So when there is a less emission, which is cooling to space, there is a change in the forcing. And usually, the negative forcing in the Antarctic has been documented before, and this is usually explained by either the near surface inversion or the temporal inversion in the stratosphere. Yeah, but as we can see in the previous slide, in such snapshot, we don't really spot near surface inversion in all the regions with negative forcing. So we will further discuss about what conditions can lead to this low and even negative forcing, and we will focus on the case in the Antarctica and the deep tropics, which are controlled by a different mechanism. So I would like to start with the Antarctica case. The figure on the left, this is the climatology of the temperature of the Antarctic in the 4 different seasons. And the figure on the right is the TOA forcing of this sounding. So basically, we see that the forcing in the Antarctic shows a very clear seasonality. the June is the only month with positive forcing, and for the other seasons, the forcing are all negative, meaning that CO2 cools the column. And we also spot that even though some literature connect a near surface inversion to the negative forcing, the December is the month with the weakest near surface inversion, but it is the month with the most negative TOA forcing. So we use a standalone RTMG, a radial transfer model, with the ERA 5 temperature and water vapor. And then we try to modify the air sounding to see the sensitivity of this air temperature structure to the forcing. So the first experiment we said is we try to smooth the near surface inversion by reducing the temperature below the 500 hectopascal while we fix the surface temperature. So basically, we see a very much similar broadband forcing, and the difference can be as small as like point something watts per meter square. So there is indeed difference, but it's negligible. And then we try to perturb the upper stratospheric temperature by reducing the temperature above 30 hectopascal and set it into an isothermal one below. And then we see that there is no longer a negative forcing in this sounding, and this temperature at 10 hectopascal effect can be very well predicted by the regression model. So how to explain this phenomena? We further examine the radiative transfer equation for the long wave part, and we want to attribute the source to a TOA forcing into the vertical structure of a temperature so that we can identify the temperature sensitivity and the forcing. So because we are looking at the instantaneous forcing, and in this equation, it shows that the flux at the infinity, which is a TOA, is the combination of the surface emission times the transmissivity, plus another term is the emission contributed by the air structure. And in this integral, the B of Z is the emission of individual vertical layer, and the WZ is called the weighting function, and we can think it as a discretized form of the transmissivity. And for the instantaneous CO2 perturbation, we assume there's no change in the air profile. So this I0 and this B of Z are fixed, and the forcing can only come from two components, which is the total transmittance, and also another term, the change in this weighting function. And to simplify the problem, we have already fixed the surface temperature, so the effect of total transmittance is relatively small. And I suppose most of people here are not familiar with this weighting function. So this weighting function is a very useful quantity in the radiative transfer. And it usually has a bell-shaped structure for the TOA flux, where the weighting function has a peak somewhere in the atmosphere. And this peak is usually called the emission layer. And we can further identify the temperature of it, which is the emission temperature, a useful quantity to understand the radiative transfer for gray atmosphere. And so it seems like we can just output all the optical information in a radiative transfer model and then calculate like the transmissivity and the weighting function. And it seems like all the problem will be solved. But the hard part is actually because in this equation, every term, I mean, the surface emission, the emission from the air, and the weighting function, all of the terms has one additional spectral dimension, which is very complicated. So I would like to first talk a bit about such a spectrally varying weighting function. The figure I'm showing in the middle, this is the spectral weighting function for a long wave for a tropical climate. So I only want to show that even though I mentioned that the weighting function is usually has a bell shape, it varies quite a lot spectrally. And for most studies discussing the instantaneous CO2 forcing, we focus on the part that are associated with the CO2 absorption band center, which is around the 670 wave number. But actually, there are some other part of the spectrum that contribute to the broadband forcing, and they are non-negligible. So to fully understand this behavior, we must consider what happens across all parts of the spectrum. And to make the result cleaner, we will later bin this spectrally varying weighting function into 3 groups according to where their emission layer locates. We will bin those into one group with weighting function peak in the stratosphere, and another group with weighting function peak in the troposphere, and another one with this weighting function peak at the surface. Yeah. So in this slide, I'm continuing discussion on the Antarctic part. So the left panel is the group weighting function for the control CO2 part. So we see that for both the red, the blue, and the orange part, we are indeed able to see the weighting function peak around the stratosphere, the troposphere, and the surface, respectively. And for the broadband one, which is the sum of all 3 different lines, they show a peak near the lower troposphere, means that most emission comes from around 500 hectopascal. But then if we double the CO2, we see a somewhat different behavior. So basically for the stratosphere, there is an enhanced weighting at around 300 hectopascal, and also a reduced weighting below. So it means that there is an upward shift of this emission layer, which is consistent with the gray atmosphere's view. And also such elevation of the emission layer can be also seen in the blue one, the troposphere group, and also the surface one. But the interesting thing here is if you sum all those 3 lines into a broadband one, you actually see some spectral cancellation below about 100 hectopascal. So eventually, for the Antarctica sounding, it is the upper stratosphere part that remains after spectral cancellation. And this and if we further group the forcing into each group of the weighting function, we can also see like for the broadband one, reduce smoothing the low level temperature inversion doesn't change much about the broadband forcing, but a perturbed upper stratospheric temperature can induce can bring this forcing into a positive. So so I'm moving on to the tropic part. So how about those low CO2 forcing in the tropics? So as a spoiler, this region with very low forcing are the region found with the very strong cloud relative effect. And this can actually be somewhat predicted from our regression model, where the all sky forcing is a combination of the clear sky forcing plus some cloud relative effect. And if we put all the number in, we can like we can use some very simple algebra and then get that if we have a strong cloud radiative effect above about 120 watts per meter square, it is possible to find a negative forcing. And you can see like the contour of the CRE at about 120 watts per meter square can actually identify the regions with negative forcing. So we perform a similar analysis as the Antarctic case. So again, the panel on the left is the weighting function for the control CO2 and the change of weighting function. So looking at this weighting function change part for the broadband one, we also see a very clear contribution from the stratosphere, but there are some like apparently reduced contribution from the air below. And for clear sky forcing, such change in the weighting function amounts to roughly 3.2 watts per meter square in the forcing. So what role does the cloud play? We plug in a very simple—
Yan-Ting, 2 minutes left.
Okay. So we plug the cloud inside, and then we fix the cloud top at 100 hectopascal, and then we further tune the depth of cloud and different concentration of the cloud ice mixing ratio. And the color on the right denotes like one parameter. So no matter what kind of parameter we perturb, we see that this change of the forcing by cloud is very well correlated to the cloud radiative effect. And when the cloud is thick enough at about 125 watts per meter square here, the broadband forcing comes to be negative. So this partially explains why in the region with very heavy cloud, we see a negative forcing. And then what happens if we no longer have such negative lapse rate in the stratosphere? So we also did another simulation, simply smooth the air temperature in the stratosphere and then set them as the cold point one. So this essentially reduced the temperature at 10 hectopascal by around 40 Kelvin. And this, from the regression model, translates to about like 1 watt per meter square in the forcing. And we can also see that by setting another set of isothermal stratosphere, this broadband forcing can no longer be a negative. So this also suggests that the reason we see that negative forcing in the deep tropics are associated with their stratospheric temperature structure. And when there is a thick cloud, the cloud is able to like mask all the forcing contributed by the troposphere, and then the stratospheric effect will be very outstanding. So for some take-home point, we show that it is possible to find some region and conditions that leads to a very low and even negative CO2 forcing. And this can be predicted by a simple model. And also, we see that the negative forcing are associated with a very warm upper stratospheric temperature by some mechanism like denial experiment. We smooth the upper temperature structure, and we also implement the clouds, and then they all shows a consistent role of the importance in the upper stratosphere. So the first part of this talk has been published, and we have another manuscript in preparation for this, and I will be happy to share when it's available. So
yeah, thanks, Yan-Ting, for a very nice talk. Do people have a quick question for Yan-Ting? If not, I think we should probably move on. Nick?
Yeah, okay, thanks. So our next speaker is Luke Davis. Um,
Hi, everyone. Can everyone see this?
yeah,
Yes.
looks great. Thanks. And Luke, you're
Great.
a postdoc at East Anglia now?
Yeah. Yeah, that's right. So yeah, I guess I'll just get into it. Yeah, I'm a postdoc at University of East Anglia. Recently completed my PhD at Colorado State University a couple months ago. And today I'm going to be talking about a project I've been working on with my advisor, David Thompson, and Maria Rubenstein and Thomas Berner on relationships between climate feedbacks in the response to increase in CO2 and internal variability. So the way I sort of think about this project, or way I've started to think about it, is there are two common threads in present day climate feedback research that are pretty rapidly growing. There's sort of the pattern effect um, um, field of research where we try to identify influence of surface warming and cloud patterns and their time evolution on the global response to CO2. And it's also a large body of work on observational constraints where we try to identify intermodal relationships between observable quantities and the global response to CO2, and then try to predict the most likely futures based on which models best simulate those observables. So here we try to leverage both of these perspectives by looking at how we can understand a relationship, an intermodal relationship between perturbed CO2-driven cloud feedbacks and observable unperturbed ENSO-driven cloud feedbacks, and how we can better understand that using warming patterns and cloud patterns. So for all the results I'm about to show, I use just simple regressions of surface temperature, that is regressions of radiative flux against global average surface temperature, so just Gregory regressions. For the unperturbed feedbacks I talked about before, they're just delta T and delta R anomalies over the full 150-year pre-industrial simulation. And for the perturbed feedbacks, the delta T and delta R anomalies are responses to the CO2 quadrupling experiments. I also decompose each feedback into cloudy sky and clear sky components. And I do this by just using all sky minus clear sky flux. We also repeated this analysis using a full kernel decomposition methodology where you adjust for cloud masking, but it did not, in this case, have a significant effect on any of our results. So for simplicity, we proceed with just all sky minus clear sky fluxes. And in these results, we also try to account for similarities between models using a really simple, just institute averaging approach where we average results across models from the same institute, because those tend to have more similar results. It's not an ironclad rule, but we found that's the case. It gives us more conservative uncertainty bounds. Again, that is also not critical to our results, but it just makes these results a little bit more conservative. So in this first figure, I just wanted to give an overview of the unperturbed and perturbed feedbacks I calculated, and that I'm going to use to assess these relationships. So this is kind of a little complicated figure. I'll walk you through it. Each shading zone corresponds to a given feedback component, and the thickness of the shapes are just probability distributions. These are violin plots. Some of you might be a little familiar with them. On the far left, it shows just the net feedbacks, the net TOA flux. The blue shapes are unperturbed feedbacks, and the pink red shapes are perturbed feedbacks. So that's 4 times CO2. And on the left, in these pale colors, that's the CMIP5 ensemble. On the right, CMIP6 ensemble. So one thing you'll notice from all these plots is that between CMIP5 and CMIP6, the unperturbed feedback spread, it's shifted down a little, but it's largely similar spread. But when you compare the CMIP5 and CMIP6 perturbed feedback distributions, there's sort of more drastic changes to the ensemble. So for the rest of this talk, we're actually just going to focus on cloud and shortwave cloud feedbacks because the effect is more pronounced for the cloud component. So if you look at the center panel here, you'll see that In CMIP5, the shortwave perturbed cloud feedback is noticeably less intermodal spread than the unperturbed feedback distribution. But in CMIP6, their intermodal spreads are quite similar. It's just shifted up. And of course, we all know that shortwave clouds are somewhat more positive in CMIP6. So this is just sort of a way to get an overview of the different distributions and to hint at what these intermodal relationships might be, what sort of constraints we might get if we try to predict the red shapes from the blue shapes. And that's what I'm going to do in this next plot I'm going to show you. So if you're looking for a constraint on the perturbed cloud response from unperturbed cloud variability, one very simple approach is to just get a linear regression of those perturbed responses onto the unperturbed responses. And then you use that regression coefficient to develop an emergent constraint. So this next plot here shows a summary of those regression coefficients. The same format as the previous plot. We're just regressing the red shapes against the blue shapes for CMIP5 and CMIP6. And as that plot implied, we see that in CMIP6, we have much stronger, we have higher regression coefficients closer to unity. And we tend to have an increased variance explained by those relationships. So if you'll just look at the shortwave cloud panel here, then you'll see in CMIP5, the slope is quite shallow. So perturbed cloud feedback spread is suppressed, and the R squared is a little bit lower. That's indicated by the percentage mark here. On CMIP6, the slope and R squared are a little bit elevated. And that result mostly holds for all these components, but for the rest of this talk, we'll just focus on shortwave clouds. So again, we're trying to build towards an emergent constraint here. And in order to do that, we got an observational estimate of this unperturbed shortwave cloud feedback by regressing series shortwave radiative flux against surface temperature. And just wanted to throw that up here just to show you guys what the time series are. Of course, everyone's familiar with this, but so we have surface temperature on the top and shortwave cloud radiative effect on the bottom. These are monthly anomalies, deseasonalized relative to climatology. And we regress the bottom panel against the top panel to get our observational cloud feedback estimate. And we also detrended both time series to try to isolate the sort of pre-industrial-like ENSO-driven component. And we also repeated this analysis for the net flux component. And we compared our uncertainty and our mean estimate to a recent result from a Dessler and Forrester paper. And our result was pretty indistinguishable. So that gave us a little more confidence in our methodology for assessing this observational feedback and its uncertainty. The only difference here is, again, we're focusing on shortwave clouds specifically. So in this panel here, we apply those regression coefficients that we derived in that bar plot, showed a couple slides earlier. And that's depicted by these black lines here. And we combine that with that observational estimate of the feedback I showed in the previous slide, the blue shading, to try to predict, to try to constrain what may be the most likely perturbed cloud feedback response, which is shown in the red shading. This is just a classic emergent constraints plot. Again, on the y-axis is the perturbed shortwave cloud feedback, and on the x-axis is the unperturbed shortwave cloud feedback. And so the x-axis is our observable, and the y-axis is what we're trying to predict. The blue line and the blue shading are that observational estimate. Red line, red shading are the perturbed cloud feedbacks that seem to be most consistent with those observations based on that relationship. So takeaway from this plot is that in CMIP5, the slope is shallower and the R squared is slightly lower. So the constraint is not very effective. The shading actually shows 90% uncertainty bound. So it could marginally reduce the perturbed feedback spread, but it's hard to say if that's particularly useful. But in CMIP6, it's a little bit of a different story because the regression line is kind of lifted and a little more certain. We find that the perturbed cloud feedbacks, most likely the observations, are now also on the higher side. So the constraint has changed with CMIP 5 and 6, which is also not really what we want from constraints, I guess, but that makes us think about which cloud processes we should believe. And it made us wonder why those slopes were so different and those constraints were so different. And those results were also surprising because a lot of past research has found pretty weak relationships between perturbed response and ENSO-driven variability, or at least relationships that are difficult to interpret and kind of subtle. And a lot of recent research has showed many other more complex cloud-based constraints in the response are less effective in CMIP6 than CMIP5. And here we found that one of the simplest possible candidates for a cloud-based constraint has become somewhat stronger in CMIP6. And again, it's just sort of, if you look on the right here, it's sort of just ruling out more scatter points there. And relative to the larger spread, it does seem to be ruling out more points. And so we try to understand the mechanisms for these differences using spatial decompositions of the relationships. And this is where the pattern effect component comes to play. So to start things off, we compare, we calculate just regional cloud feedbacks using a pretty common method. We regress global shortwave cloud effect flux against global average surface temperature. And that gives us local climate feedback. If we take the global average of that metric, we just retrieve the exact shortwave cloud feedback definition that I showed a couple slides ago. And this is what the average shortwave cloud pattern looks like between CMIP 5 and 6. On the left is CMIP 5, right is CMIP 6. They're pretty similar, but in CMIP 6, you can see there's just a sort of more intense tropical pattern for these cloud changes. And in CMIP 5, the shortwave cloud contribution in the Southern Ocean is also a little bit weaker. So it gets more red between CMIP 5 and 6. And so you can see there's sort of a role for both the tropics and the Southern Ocean here. And this is just to sort of qualitatively show what these patterns look like, first of all. When we compare those perturbed shortwave cloud patterns on the top here to the unperturbed patterns on the bottom, we find that unperturbed feedbacks consistently have that sort of strong tropical ENSO-like pattern. And in CMIP 6, if you kind of squint, like on the top right, it's somewhat more similar to that unperturbed. But this is all qualitative, so we wanted a more qualitative metrics. So in these next figures, we wanted to exactly decompose those intermodal regression coefficients I showed previously. And we did that using a technique. I think a few people have used this before, but we basically regress our perturbed quantity that we want to predict onto the global average unperturbed quantity. And that gives us a map of the regional contributions to the intermodal regression coefficient. So in these next plots, I'm going to show you if you just take the global average of the shading, you get one of those regression coefficient bars that I showed in a few slides ago. And so that's shown here. And we were struck by pretty strong differences between CMIP 5 and CMIP 6. And CMIP 6, even in this intermodal regression coefficient pattern, we sort of see this ENSO-like pattern. We have that Central Pacific and East Pacific strongly contributes to the intermodal relationship, as you'd expect if it's sort of a closer relationship with ENSO. And also the Southern Ocean kind of lights up down here. So Southern Ocean is also positively contributing to the regression coefficient between perturbed and unperturbed. you compare that to CMIP5, you'll see that the tropical signal is kind of more muddled and harder to interpret. And notably, over the Southern Ocean, the sign has changed. It's not really contributing at all to the predictability of the response. So that was a pretty large difference. And if you compare those contribution plots to just the unperturbed pattern contributions, then you also find that in CMIP6, the late perturbed pattern somewhat more closely resembles the unperturbed pattern than in CMIP5. So the same places that are contributing to increased predictability of these, or increased strength of this regression slope for the perturbed CMIP6 response, those same regions are responsible for increasing the magnitude of the unperturbed, just the global unperturbed cloud feedback between models. These figures are a little complicated, so I'm not sure all of that. Maybe I didn't have time to sink in, but the core point is just CMIP6, CMIP5 are quite different there. And just a couple more results slides here, and then leave you guys with conclusions. So in this plot, we wanted to try to understand these relative roles of the Southern Ocean and the tropics. So we took the zonal average of those previous figures. On the far left is CMIP5, and middle is CMIP6, and far right is their difference. So again, these are regional contributions to the intermodal regression coefficients. And we see that in CMIP5, there's sort of the tropics are sort of broadly contributing to that relationship, but in CMIP6, there's just this huge role for, there's this huge contribution from the tropics, and there's a similar spike in this over the Southern Ocean. So both of these regions are responsible for elevating the regression coefficient between unperturbed and perturbed CMIP6. And this last slide is a little bit different from the slides I showed you previously, but we just wanted one metric to just emphasize how different CMIP6 is from CMIP5. So here we took the intermodal correlation coefficient between tropical cloud feedbacks and Southern Ocean cloud feedbacks. So we just wanted to understand, like, if a given model has higher cloud feedbacks over the tropics, does it also tend to have higher cloud feedbacks over the Southern Ocean? And we were pretty struck by this. You see in CMIP5, there's almost no intermodal correlation. It's quite weak. And CMIP6, all of a sudden, especially for the shortwave component, models with more positive tropical shortwave cloud feedbacks tend to have more positive Southern Ocean cloud feedbacks. And my advisor is Dave Thompson. He's been Amethyst, so was sort of trained in large-scale dynamics, transitioning to this sort of feedbacks in cloudy, cloud world. So I'm not really sure what to make of it, but hopefully that stimulates some interest and maybe discussion, because this result was pretty surprising to us. Yeah, it's important to establish physical mechanisms for interpreting emergent constraints, and the above results point to, as I've been sort of talking about, perturbed cloud feedbacks seem to be more closely related to unperturbed when the El Nino-like patterns project onto ANSO-driven variability. And we expect a fluctuation dissipation mechanism may help to explain this. If you just tend to have more warming in the East Pacific as you get with the late response, then you'll tend to have a increased relationship between internal and the perturbed cloud responses, and that seems to be somewhat amplified in CMIP6. And we also found that the Southern Ocean cloud responses seem to be somewhat less distinct in CMIP6 than CMIP5, and compared to these tropical cloud responses, and that's contributing to this huge difference in this constraint. And with that, I'll just leave everyone on this conclusion slide. I think I'm running out of time, so thanks for your time.
Thanks, Luke. We have some time for questions. So any questions for Luke? All right, we got one in the chat from Andrew. So CMIP6 models tend to have a stronger El Nino like warming under absorbed 4 times CO2 than CMIP 5 models. Do you think this can explain why perturbed feedbacks in CMIP 6 look more like the unperturbed ones than in CMIP 5?
Yeah, I believe so. Yeah, the warming pattern contributions. Yes, I think that's contributing to it. And yeah, it's the Southern Ocean clouds that seem to be a little, I don't understand quite as well. I know in the Southern Ocean, this mixed phase cloud, strongly negative mixed phase cloud feedback has been muted in CMIP 6. But I wonder if that was like a distinct extratropical thing that's more muted. So now the cloud responses are all sort of going in a similar way to internal variability, but that's very like fuzzy. But yes, I think the warming pattern likely plays a role. And we also did these complicated warming pattern regressions, which I don't think I have time to explain, but we'll have some figures in this manuscript we're preparing that support that.
Yeah, you can chat more in the chat. Yeah.
Thanks.
Okay. Yeah, thanks, Luke. That was a really nice presentation. Our last speaker today is going to be Tim Merlis, who's now at Princeton. And I think this is going to be a bit of a change of pace.
Yeah. Okay. Thanks, everybody, to the organizers in particular, and thanks for sticking around. I'm going to talk about simulations of climate change and global storm resolving model. And this is a big collaboration with folks at Princeton, Geophysical Fluid Dynamics Laboratory, and the Allen Institute for AI. Kai-Yuan Cheng is highlighted as the second author who ran these simulations, which are big. Okay, what is a global storm resolving model? This is a category of model with kilometer scale horizontal resolution. There's been a recent intercomparison project called Diamond, where a number of these models were compared for short integrations, roughly 1 month long. The history of this class of model goes back maybe 20 years to Earth simulator work in Japan, but it's becoming more commonplace. And so we're going to explore climate changes in these simulations, which were done using GFDL's X-Shield model. And one really distinctive thing is that we've looked at 2-year-long integrations, which allows for some climate relevant investigations. And the high-minded philosophy, that's a bit tongue-in-cheek, is we're going to compare this global storm resolving model simulation of climate change to GCMs, conventional climate models, and we'll see if they're within the range of models. And if they are, well, that's reassuring. We know GCMs rely on subgrid scale closures like convective parameterization, whereas these kilometer scale models are explicitly simulating at least the large scales of moist convection. So that's a known uncertainty, and it's more of a direct or explicit simulation of those important processes. Now, if these GSRMs are not in the range of GCMs, well, that bears further attention. Maybe there are physical reasons why GCM behavior is sort of not representing the response to warming, or maybe there's more work to be done developing this sort of new class of high resolution atmospheric models. Okay, X-Shield stands for the experimental system for high resolution prediction on Earth to local domains. This is developed at GFDL and is a sort of cousin of NOAA's operational numerical weather forecast model. Simulations I'll present here have about 3 kilometer horizontal resolution and no deep convective parameterization. So the deep convection is explicitly resolved, and there's still a shallow convection scheme. The lower boundary condition is a nudging scheme that brings the SST towards an analyzed product. And these are performed on Princeton University's Stellar Cluster. This is a really distinctive high performance computing platform that we're making use of to do this sort of unprecedentedly long storm resolving model simulation. Okay, I'm emphasizing it's long, but 2 years, is sort of short compared to conventional AMIP protocols where you might have 30 plus years to look at, but it's much longer than that Diamond intercomparison protocol of 40 days. We have 4 simulations. I'll present the results of some of them. A control simulation, a uniform SST warming with unchanged CO2 and radiative forcing agents, and increased CO2 simulation with unchanged SST and a combined sort of climate change simulation. The uniform SST is, of course, an approximation, a simplification, and there's well-known, well-understood issues with that, but simple things come first. And the analogs of these in the CMIP, CFMIP simulations are the AMIP experiments, AMIP plus 4K, AMIP 4X CO2. In CMIP 6, there's about a dozen GCMs that have these 3 experiments. So that's the comparison I'll be doing. What do you do with these really computationally expensive, beautiful simulation of moist turbulent flow, comprehensive Earth boundary conditions? One thing you can do is you can make a visualization like this one I've showed on a few slides of just vertically integrated cloud ice and liquid water to show the incredible detail that we're simulating on a global domain. The other thing you could do is the opposite limit, which is take the global mean and consider the change in the top of atmosphere radiation balance, the radiative forcing, and the radiative feedback parameter. Now, why would you do that? I don't think I need to justify that too much to this audience, but this is the $1 trillion question of climate science. And I think it's incumbent upon us to immediately investigate this. So that's what I've done here. And I'll start with the climate sensitivity and the factors that underlie it. So the CES sensitivity plotted here in the X-shield simulations with the red stars. I don't know if you can see my mouse, but the red star is X-shield. And then the colored symbols are CMIP 6 models with the gray line indicating estimated distribution, a violin plot. Here, the CES sensitivity is the top of atmosphere net radiation change in response to uniform warming. You can express that as a feedback parameter or assume a radiative forcing and express that as a climate sensitivity, which is what's shown here. You can see X-shield is at the heart of the CMIP 6 distribution. The CES sensitivity is about 2.2 Kelvin. I'm assuming the same radiative forcing for all models, and I'll revisit that later. You can split between long wave and short wave, and the long wave of X-shield is basically the same as the total, and so that means there's a neutral short wave feedback. In CMIP models, there's a positive destabilizing short wave feedback. So at least at first glance, the implication is that this GSRM has similar robust clear sky feedbacks and maybe cloud feedbacks that are within the range of the GCM spread. Let's think about what underlies those robust clear sky feedbacks. One is the temperature change distribution. Here we're looking at the annual and zonal mean temperature change of X-shield on the left, CMIP 6 on the right. You can see well-known expected features, upper tropospheric amplification. Because of the uniform SST perturbation, there's not too much spatial structure of the surface warming. Overall, these are pretty similar. I'm not going to say more about that. In contrast, I want to focus on the relative humidity change. In the global mean, the relative humidity change is near zero in climate change projections, but underlying that near zero are robustly simulated changes in the zonal mean relative humidity. This goes back at least to CMIP 3. The pattern is something like a horseshoe pattern of reduction in relative humidity, going from the tropical upper troposphere down to the mid-troposphere and the subtropics and mid-latitudes. Above that, near the tropopause, the climatological tropopause is a region of increased relative humidity. That's because the tropopause rises, and in doing so converts what was formerly stratospheric air into upper tropospheric air. There's also this feature in the mid-troposphere of the deep tropics of an increase in relative humidity. The magnitude of these is small. It's like 1% per Kelvin order of magnitude. And you can see X-shield on the left-hand side behaves quite similarly in this really kind of a subtle pattern of relative humidity change. So was that inevitable? To turn to that question, should we have expected it to this resolution with explicit simulation of deep convection to behave similarly to GCMs? I want to turn to results from the RCEMIP intercomparison project. The picture on the right-hand side is showing an analysis of the mid-tropospheric relative humidity response to warming from Becker and Wing. And you can see that there are models that have reductions in mid-tropospheric relative humidity of order 2% per Kelvin in the radiative convective equilibrium change simulations. on the right-hand side, simulations that have increases in relative humidity of something like 2 or 3% per Kelvin. And those models, which are the CRMs typically, have nearly neutral long wave feedbacks, or sorry, neutral is the wrong word, it's destabilizing, right? It's the boundary of the runaway greenhouse. So that should be alarming, right? If that was going on in the real world, that would be a big deal. And interestingly, X-Shield is reassuringly similar to GCMs. So that's suggestive of large-scale control on the relative humidity changes, rather than some, sort of fundamental difference from explicitly resolving deep convection. Okay, last result is, let's look at the effective radiative forcing. So this is defined as the TOA flux change from a CO2 increase with unchanged SST. Again, we're looking at CMIP6 in the distribution on the left and X-Shield on the right. You can see that the ERF in X-Shield is outside the range. It's more positive than any CMIP6 model. And that's not because of some interesting shortwave adjustments. So comparing the long wave and shortwave, comparing the long wave and total, you can get a sense that X-Shield, like CMIP6 models, has positive shortwave adjustments, increasing the forcing, but the long wave itself is quite high in X-Shield. So what's going on there? This is preliminary analysis done with Max Below, and we're looking at the factors that might account for this very high, relatively high long wave effective radiative forcing. One factor is that the climatological cloud distribution of X-Shield has biases. So the solid line here on the left is showing X-Shield tropical ice clouds. And you can see that the peak in the high cloud fraction occurs at higher pressure, i.e. Lower altitude than these two satellite observation estimates. So that's sort of going to lead to a bias in the cloud masking and a higher CO2 forcing. Now, these GSRMs are very expensive to run, so they're less well tuned than conventional GCMs. The model was sort of frozen before a long simulation was run, and so, okay, that's something that could be revisited in future development. On the right-hand side is something that I find very interesting and worthy of follow-up, which is that the high cloud adjustment to the forcing is an increase in high clouds. We have sort of two baselines here. One is a control SST, one is the increased SST, about which we increase the CO2. And in both cases, there's a tendency to get more high clouds, more ice clouds in the upper tropical troposphere. That's going to increase the CO2 radiative forcing. And that's, more explicitly simulated than GCMs would do. So that's intriguing, potentially concerning reason for a higher radiative forcing. In summary, the X-Shield GSRM has assessed sensitivity that's in line with conventional climate models. Why does that happen? Basically, the relative humidity change is quite comparable to conventional GCMs. And that's important for radiative feedback analysis. That's sort of the null hypothesis that underlies the now conventional feedback approach. And I want to emphasize that that's not trivial or inevitable. Don't shrug off the similarity of this GSRM with GCMs. RCE MIP simulations don't clearly behave that way. The effective radiative forcing of this model is high. It's outside the range of CMIP6 models. And there's this really interesting direct response to CO2 of an increase in high clouds that bears further scrutiny. I'll note that the next phase of this diamond intercomparison project will include warmed SST simulations, but it will not include increased CO2 simulations. So whether this is sort of a one model result or more robust is something that's going to be hard to tell in the near future. Thanks so much for your attention.
Thanks, Tim. So there are some discussions going on in the chat. Any questions for Tim?
I'll end with a Manabi quote if there's no question. Here's something Manabi said in March. Somebody asked him about what he thinks about GSRMs, and he understood the question, and he said, don't make the model more complicated, just increase the resolution, and what comes next? I think you'll have great fun. So That's a sort of an endorsement from our favorite Nobel Prize winner.
Yeah, we got one from Claire Singer. Have you calculated any metrics for convective aggregation for further understand the RH changes you see in the X-shield?
Yeah, we have computed some convective aggregation metrics, and frankly, the preliminary results I find concerning from the perspective of robustness across metrics. We don't get the same results for the different metrics that have been proposed in the literature. And so I think as a community, we should be really careful when people market big changes in organization using one metric. It's not clear that there's robustness. And, this is an interesting type of simulation to look at those metrics because we have clearly like convective scale processes, but we also have those large scale circulations. And so things like the subsidence fraction may be more reflective of large scales, Hadley cell, Walker cell changes. Things like I-org metric may be more indicative of convective scale changes. And so maybe it's reasonable that those things can potentially go different ways. But the changes aren't clear across metrics, and so we're kind of hesitating to market those as a big deal. Other people may take different approaches and really highlight a given metric changing.
All right, there's another one from Yi Huang. Was the instantaneous forcing in X-shield run computed? Do you see anything interesting?
Yeah, so we don't have an instantaneous forcing calculation. A lot of my thinking relies on sort of Yan-Ting's regression models as a sort of start. But we haven't actually done a sort of proper detailed instantaneous forcing calculation to see, how much of this long wave forcing being high is coming from adjustments versus just, sort of the control distribution could have some biases in the climatology that affect the forcing in the instantaneous forcing.
Thanks. I think it's about 1 hour. Yeah, it's a good time to wrap up here. Thanks everyone, and thanks especially for our speakers here. 3 great talks today. If you have any questions, you can email them, and we'll also put the recordings on the website as well as the questions and discussions in the chat.
And again, if anyone is interested in joining the organizing committee, please get in touch. We're looking for 2 new members.
Yep.
Bye, everyone.
Bye-bye.
Thanks. Bye.